the properties of power spectral density, and then we started discussing about the white noise, its properties. So so we actually need the knowledge about the white noise, power spectral density, all those concepts to understand the power of frequency components in a certain signal, and then try to remove the effect of the white noise in some cases, and only obtain the required signal that we want to achieve. So, I mean, when you consider a phone call, once it is getting transmitted from a mobile device to a base station, and from a base station to another mobile device, the signal gets impacted by different, environmental conditions, noise signals. So because of that, we receive a distorted signal at the receiver end. Once we receive that, we need to somehow decode the information from the noise impacted signal. So the received signal has a lot of noise. So in order for us to know the like what noise looks like, we need to know how noise is shown in the frequency domain and in the time domain. So in the frequency domain, we can see that the noise has these characteristics, where the power spectral density of the noise over all frequencies will be roughly a constant value, which is about n0/2. And then the autocorrelation value of the white noise will have a value only at the 0th position, where it means that there's no autocorrelation between any 2 points in the white noise. Only the value is there only with that same time instance. So which means that once you consider tau means the time gap between 2 points in the time series. So if there's a time gap between 2 points that we are evaluating, then there's no correlation in the white noise. If we are considering the same point and comparing the same point, then there is a correlation, and that is the only correlation that we can find. So the value of the correlation that we find will be infinite in the for example, in the continuous time domain. In the discrete time domain, it will be equal to 1. The total area under the curve for the autocorrelation will be, the total area under the curve will be 1 when you consider the power. However, like when you consider the autocorrelation function, you will be having the magnitude of 1 in here. For when you consider the delta function will have a value of 1 when tau is equal to 0. The magnitude of the autocorrelation will be basically delta into n0/2. So the magnitude in here will be n0/2. So delta into n0/2 gives n0/2 at 0th position only, and the value of autocorrelation will be 0 at every other position. So those characteristics we have to identify in the received signal in order to identify the noise impact in the received signal, and to remove that using some methods. So when we I think we tried to convert the white noise into we try to find the autocorrelation value of the white noise for a limited bandwidth noise. So when the bandwidth of the noise that we are considering is limited, we call that bandwidth limited white noise. In that we can find the autocorrelation value. That one we found in this in here. So we found that it was like a sinc function, and that function is depending on the bandwidth of the white noise. So after that, the linear time invariant systems is what we started discussing. The linear time invariant systems are actually used to consider applications where we will be processing a certain input signal that we receive. So normally we will be applying the knowledge that we have about the random processors to maybe decode any kind of a signal that we receive at the input. So if you consider um, like maybe wireless communication scenario, the original signal that we are transmitting can be considered as xt, and then you're transmitting it through a certain signal channel. There's a channel in between the receiver end and the transmitter end. So that channel will have a certain characteristics, and that characteristics will determine the transfer function of the channel. And then the output will be obtained as YT. The output will be the received signal, and from the received signal, we need to find out the original XT value. So we will be measuring the YT, and we want to find out what XT is. So normally that would be one of the cases where we need the studying of systems or linear time invariant systems to identify original signals. So linear time invariant systems are therefore what we are going to discuss, and we are going to find out details regarding how we can define the statistics of the linear time invariant system. So after you define the statistics, you can then you can find different parameters. So as I said before, we our one of our main targets is trying to find the original data. So once we receive some measurement, we try to find the original data. So that is done using estimation techniques. We have different estimation techniques. Linear mean square estimation or mean square estimation, we call that MSE. It's called as square estimation, mean square estimation, and there's also something called minimum mean square estimation. So other types of estimations are also used. So we will be discussing about how we can use those estimation methods and what are the principles behind them. So we have to actually do some assumptions when we are doing the estimations. So due to the assumption, sometimes the estimation might not be exactly same as the original signal, and therefore there could be some error between the estimation and the actual signal values. So basically, about the linear systems, we discussed about how we have the properties defined. So the linear systems means that the properties of the system is uh, such that the once you give some inputs to the system, uh, if it is a linear system, the transfer function can be applied to each of the different signals that were applied to the system um, as a combination, for example. So if we input a signal, input two signals, and I mean as a combination, we can consider that the actual output will be a combination of transfer function applied on each of the two different signals in the input. So likewise, linear systems means you can add the transfer function effect onto each of the individual components of the input signal. Time invariant means that if there is a time invariance is another property of the time invariant system. So time invariant means that if you add a certain delay or a phase shift or some kind of a uh, shift in the time, then the output also will be shifted in the same amount. So if that is happening, then even though you have a delay at the input, then y also will, or the output will also reflect the same delay. And such kind of systems we define as time invariant systems, which means that delay in time applied onto the input does not affect the output of that corresponding signal. So that was basically regarding time invariant systems. So combination of linear and time invariant properties give us the linear time invariant system. So in this module, we will be basically focused on linear time invariant systems. So we will be analyzing their properties basically, and we will be considering such kind of systems most of the time. So in these kind of linear time invariant systems, we want to find out the impulse response or the transfer function of the system. So in order for us to find the transfer function, we use the impulse response of the system. So what I mean by that is that we give as input an impulse to the system, and we observe the output. So the output that you obtain once you give an impulse to the system is known as the impulse response, right? So if you have a normal system where you have the input xt and output yt, and you want to find out what t is, transfer function. So currently, uh, like once you have all these things, you have to know everything except the transfer function to find the transfer function. So if you are giving some kind of impulse at the input, which is a known signal, you can create it. An impulse you can create some, voltage spike or some kind of uh, sudden change in voltage at the input, and then you can try to mimic the delta t, and then you can get some kind of a measurement at the output. So in this situation, you can measure, or you can measure the output, you can give the input. So because of that, this kind of a setup can be used to find the transfer function of the system. So once you have the impulse response and once you know the input, you can use those things to find the transfer function uh, uh, by uh, by uh, by mathematics. So the another thing is that uh, so actually after you find the impulse response, you can actually consider uh, you can actually consider the impulse response as the transfer function of the system. So because impulse response is the um, the fundamental way that the system behaves under an impulse. So for any other types of inputs, the system will behave according to the way that the system behaves under the impulse response as well. So the HT is taken as the impulse response, and basically the transfer function of the system for the linear time invariant systems. So for linear time invariant systems, you can consider that impulse response as the transfer function of the system. The linear time invariant systems, therefore, you find the transfer function by using the impulse response, and then once that is known, you can actually consider that as the transfer function of the system. mainly because of the properties of the linear, properties exhibited by the linear time invariant systems. So because it's linear, because it's time invariant, you can consider that the transfer function of the system behaves according to the impulse response. The input signal that you provide can be therefore uh, actually we can since we know the transfer functions, we can therefore find any relationship between the input output signals and the transfer function of the signal, those things. So in linear time invariant systems, you consider you consider an impulse, and then you find the impulse response. So the impulse response is taken as the transfer function of the system. It represents the behavior of the system under an impulse, and also it can be considered as a way that it will behave. Way that the system will behave under any input. So because of that, HT is the representative of the transfer function of the system. So HT is the transfer function of the system. So since if you can find that, then other things related to the system can be found. So when you consider the linear time invariant systems, we can also consider two other things, which are like you can consider the system in the time domain, or else you can consider the system in the frequency domain. So in situations, you sometimes cannot, observe the properties of a system only in the time domain. Such as, for example, you can't see the frequency. You can't see the frequency by just plotting the signal in oscilloscope. For example, you can't see the frequency there just by itself. So sometimes you need to see the signals through the frequency domain. So seeing in the frequency domain allow us to see the frequency of the signal, the power of the frequency components, the harmonics that are there in the signal. So unwanted frequencies, whether they are there or not, whether there's some noise in the signal. So those can be clearly seen if you get that signal that you're going to observe under the frequency domain. So because of that, most of the time we have both the time domain analysis and frequency domain analysis. So if you are doing time domain analysis, you will be considering time domain signals, and the relationship between the input output of a system will be according to the here. So we'll be basically doing convolution between the impulse response and the input signal xt to find the output of the system. So convolution operation has to be done between the impulse response and the input signal. The thing is that convolution is a costly task, although it is the conventional task that should happen. It is a costly task. So when you have convolution, you have to do integration like this, where you are taking the product between the impulse response and the input signal by considering all the possible different time lags between the signal. So between the two signals, you have to consider time lag. Then you have to consider the product between the the impulse response of the transfer function and the input signal. So once you're doing this integration, it's actually a little bit of computational costly task. When you're considering frequency domain, however, you only have to consider the multiplication between the frequency domain version of the transfer function and the input signal that you're considering. So the product operation is actually simpler than convolution operation. So multiplication is easier and less costly. And when you're therefore doing some work related to getting the behavior of a system with its transfer function and input signal, then sometimes you can consider them in the frequency domain and get the calculations done very efficiently. So the HF here is the Fourier transform of the impulse response. The Fourier transform of for a certain signal can be found by multiplying the time domain signal with its e to the minus j2 pi ft. So you can multiply with the exponential, which is given by e to the minus j 2 pi ft. So 2 pi f means the omega of the signal, or else you can actually define it as 2 pi f. So with this operation, you can find the Fourier transform of any signal. So in here, we can find the Fourier transform of the impulse response, and we can find the capital HF. So for a we considered the linear time invariant system for a wide sense stationary process first. So wide sense stationary processes are quite, I mean, kind of interesting process because it has its second order statistics a constant over time. So what I mean by that is the second order statistics do not depend on specific time instances. It only depends on the time gap between 2 points. So most of the time, I mean, either the time gap between the two instances or else it could be a constant. So if you are considering the mean value, variance value, those things will be constant for the wide sense stationary process, and it will not depend on the time instances of the process, specific time instances of the process. If you are considering autocorrelation, autocovariance, those statistics actually depend on the time gap between 2 points in the time series. So anyway, like because they are not depending on specific time instances of the random process, because of that, they are known as constant statistics. Because they are constant over like that, it is a wide sense stationary process. When you're considering the wide sense stationary process, then you can evaluate the output of the wide sense stationary process, and then you can find out how the average value average value of the output changes once you know the average value of the input. So if the average value or the mean value of the input is a known value, and if you are asked to find the mean value of the output, you can find it using the transfer function relationship between the input and the output. So in the last class, we have defined that once the output is like, I mean, once we find the output, we can see that the output average value is also constant. Also, I believe that if you try to do this, the autocorrelation of the output, which is given in here, is also not depend on specific time instances. It will depend on the time gap between 2 points, or else it will be a constant value, which means that the autocorrelation value of the wide sense stationary process is also a constant value, which does not depend on the specific time instances. It is constant, or else it can depend on time gap between two instances of the time series. So because of that, that autocorrelation value also is a parameter that does not vary with the specific time instances. Because of all those reasons, the output YT is also a WSS process, or a wide sense stationary process. So I hope it is clear to you. So if the input is a wide sense stationary process, then the output is also a wide sense stationary process. So so what we have to do here is that we have to show that the autocorrelation value is not having any impact with the specific time instances. So if you are mathematically showing this, you have to show finally that the expression that you obtain here does not depend specifically on the simple t, it can depend on tau, or else it can be a constant. So I think in the last class we discussed those things mainly. Uh, right. So when you're considering these kind of LTI systems, the one other thing that we need to identify here is that uh, let's say this one. So once what we see here is that the xt is a kind of a random process, right? So it's a wide sense stationary random process. This is one random process, and the output that you obtain is also a random process that you obtain. So once you are considering those two as two random processes, they can be totally different random processes. So when we are going to find out different statistics of a system, we need to know the relationships between these x and y random processes. Also, we need to know several statistics such as the mean value of the output of the system, and then we can find the variance of the output of the system. After that, we can find the relationship between xt and yt, uh, which we can find using correlation statistics, covariance statistics. So today what we are going to focus is first is on that, about the autocorrelation metrics of a random process based system, right? So I think that's important, so therefore I will discuss about that first. After that, we will discuss about a little bit about the how we can discuss about the systems again, linear time invariant systems, and how we can solve some examples. And then we will discuss about the Fourier transforms, Fourier series, how they are defined in theory, and then we will try to see maybe some simulations related to that using Matlab. So with that, I think we will start. So up to that point, do you have any questions? Okay, so also I want to mention about the assignments. So I think I have uploaded a new assignment in here under week 9. So you can complete that assignment. So this is about the random processes. So the deadline is 6th of February. So 1 month from now. So complete that, and instructions are given in here. You if you have any questions, you can send an email to me and request information. So any other information given in here in the instruction sheet. Anyway, like submit the answers to these questions in a PDF and submit the PDF to the LMS. Okay, so I think when you have a certain random process, you can actually get infinite amount of data from it. But with the equipments that we have, we can only measure finite size samples. We can only measure finite size data uh, from that signal, right? So whatever the signal that we get from a, let's say, a random process, you will only be able to measure the finite signals, finite samples of that signal. So whatever the xt signal that you obtain, it could be the original signal, um, and the original signal can have infinite samples, but with our measurements, we will only be having some, finite number of samples of the signal. So we will not have infinite number of samples. So if you consider xt, which is the input of the signal, and if we consider uh, xt as a m-dimensional or a finite sized vector, dimensional random vector, we can uh, write that as like let's say if we denote xt, we can also denote xt as xn. Let's say we are going to denote the time indexes using n, right? So instead of time indexes from t1, t2, t3, likewise, we are going to use n as the time index. So same concept actually. ton, we can actually use inter without any problem. You can use instead of t, you can use n. So n is the time index that we are considering. So the time index can be finite. I mean, can be time index can be a value which is uh, which is finite. I mean, there could be finite time samples. So in here, we are going to consider like finite time samples. So we are only having a number of samples that we can count. So let's say we have m number of samples. M-dimensional random vector has m-dimensional samples. So up to point where we have n minus m plus 1. So there will be m samples in here, and uh, basically the samples can be defined like this. So in here I have used this I mean kind of definition. So this triangle I have used to show that this m-dimensional random vector can be defined as xn equals this xn minus 1, xn minus m plus 1. So there will be m samples inside this vector. So this vector I can define like this. So if needed, I can take the transpose of this to get a column vector. Then I can find the mean value of this vector. So, right. So we are going to find the correlation. So before finding the correlation, I mean, I'm just going to just find the other statistics as well, which is mean, for example. So you can add the mean for mean or expectation value for each of the singular components of the vector. And you can define that the mu value of uh, the vector is the mu value of each of the different components. In here, I think I'm going to use capital M in here. This is capital M. So mean value you can define for the vector like this. If you are going to find the cross correlation or correlation values, in here actually we will first consider the autocorrelation value, which is given by the let's say capital R XX, and uh, we can define that as the expectation of uh, the signal components, right? So in here, since I will get some confusion between this xn and this xn, I will denote the vector using capital Xn. So this is capital. Then xn x into x transpose will be the autocorrelation value. This is the autocorrelation value of the xn signal or the vector, right? These are vectors, finite size vectors, and you will be getting the product of the vector with its transpose, and it will give us the autocorrelation value of the vector. So when we are doing this, you will actually you will have a matrix at the end. So when you are multiplying a vector by its transpose like this, you will get a vector, sorry, matrix finally. So final will be a vector. So this will result in a, sorry, matrix. This will result in a matrix. These are vectors. So we will expand that to, we will expand this further to see that. First, we are having a column vector. The column vector we can define xn minus 1, then 3 dots, and then xn minus m plus 1. These are the components of the vector. So this is a column vector. When you are multiplying with the transpose, then you are multiplying with the row vector. xn minus 1 up to xn minus 1, capital M plus 1. So in here you will have, once you do this multiplication, you will have a matrix. Anyway, you have to keep the expectation operation intact. So you can, maybe you can add the expectation operation after the multiplication. So basically you will have all these inside the brackets of the expectation. So once you do the multiplication, you will have a matrix, and that matrix will look like this. So expectation of xn into xn x transpose n. Then so since expectation is a linear operator, I will put expectation operation into each of the elements that I get once I multiply these two vectors. So I will put the expectation operation to each of the separate terms. So if I'm making some mistake in here, you can let me know. So you have to multiply. So all these components will be expanded, will be like that. You have to take the multiplication basically, and final component in here will be xn into x transpose n minus m plus 1. So the final component will be coming by the multiplication of this with this. So this will be that. So once you get these two products done, will be stored in here. We have to find the expectation value. Similar things you can do for the next rows as well, and then you can find the autocorrelation matrix. So this is the second row. Second row comes by multiplying the second row of the column with each of the elements in the row vector. Once you go to the bottom, you will be able to, I think we will be able to write the last elements. So the last element, last row comes from this multiplied, sorry, this one multiplied with these each individual component in the row vector. So we multiply this one with xtn. I have to put the expectation, then expectation of xn minus 1. Sorry, n plus 1 into x transpose n minus 1. Finally, you will have a term called x n minus m plus 1 x transpose n minus m plus 1. So you will get expectation of the product that comes once you multiply these two factors and take the expectation. This is that last one. So if you consider this autocorrelation matrix, it's actually kind of very general. It's for any kind of a process. If you consider WSS process or a wide sense stationary process, this matrix will look very organized and very very clear because it has some kind of special properties. So this is for any kind of a process. If you have a wide sense stationary process, then the autocorrelation matrix will be based on that processor's properties. So if the random process is a wide sense stationary process, you will have uh, a very symmetric matrix. So I will denote the autocorrelation as using simple R value. So in here it's not gamma, it's R. Rxx, I would say the tau value I can denote using 0 in here. So in here, in the previous case, in the first element, we have uh, autocorrelation between the same time instances or same time index n. So the autocorrelation value or the R value is computed between the same points. Because of that, the tau is 0. So Rxx 0. So this corresponds to Rxx 0. So this corresponds to Rxx 1 because there's one the gap between the two time instances is 1. Then once you take the subtraction between these two time instances, you can find the time gap between the 2 points. So this is the second one is corresponding to the RXX1. Third one is corresponding to RXX2. Likewise, we will have RXX up to M in here. When you are subtracting n minus n minus m plus 1, you will be able to uh, get uh, the gap as m, m it should be m. So I think should be so when we substitute the total number of samples of m into this expression, this final expression will be x1 in here, which corresponds to the first time sample of the signal. So when you're considering the autocorrelation value and you're subtracting the 2 points, you will be left with m plus m minus 1. Uh, so anyway, we will write this like this. So when you're having a process of m by 1, you will have autocorrelation in here, which is related to m minus 1. I hope it is clear to you. When you're considering the random process in here, the time gap between the two samples we are considering is found by subtracting n by n minus capital M plus 1. When you're doing that, you will be remaining with capital M minus 1. So the autocorrelation value will be RXX M minus 1. So this is what you will be getting for the first row of the autocorrelation matrix. And so actually even so whether this is uh, even if this is WSS process or not, this is the standard way of denoting the autocorrelation matrix. So similarly, you can find the autocorrelation value between points in here, which will be RXX1, RXX0. Likewise, you can find the values. You can denote the values of the autocorrelation using autocorrelation definition. So you can do similar for all the rest of the terms. So xn minus 1 minus n minus m plus 1 means in here it's m minus 1, m minus 2. So likewise, you can continue writing those samples until you get something called RXX0. And in here you will get RXX, so m minus 1, RXX m minus 2. Then you will get some matrix like this. So this is the standard format of autocorrelation matrix. Autocorrelation matrix look like this. Standard, format of that you will standard way of defining this will be like this. So basically this is the autocorrelation matrix. Similarly, for other matrices we can define like autocorrelation or correlation matrices. You can define correlation matrices between two different signals as well. So X and Y you can consider, and you can define the correlation for the X and Y. If it is a wide sense stationary process, then the properties of that matrix, autocorrelation matrix, is going to be very, very different or special. So if it is a so before going forward, I want to mention this autocorrelation matrix is of dimension m into m. So in here, the number of samples that we had or of the original input signal was m samples, right? So each row will have m components. Each column will have m components. By considering those things, we can say that the final matrix is a m by m matrix. So this is a m by m dimensional square matrix. So in here, we are actually having a square matrix. When we are considering the WSS process or wide sense stationary process, we can see special properties of this RXX matrix or the autocorrelation matrix. So if it is a WSS process, the autocorrelation matrix will be uh, will be showing these characteristics, mainly the values of the autocorrelation, values of RXX will not depend on time. Depend on time, which means basically that the values of RXX will be constant. Values of the RXX will be constant. But if the values you get here will not be depending on specific time instances, rather it will depend on the time gap between the points considered to find the autocorrelation value. Then also the uh, matrix will be very symmetric. It will be complex symmetric, we call, considering also the complex values of the signal. If we have complex signals that we are considering, then that matrix will have complex, complex properties and complex signals, and therefore we denote them using complex numbers. So that matrix will be complex symmetric. If it is a normal symmetric matrix with real numbers, then it will be symmetric. So anyway, what I'm saying is that the autocorrelation matrix will show symmetric properties. So it will be a complex symmetric matrix, and it will therefore be something known as a Hermitian matrix. Hermitian matrix. Hermitian matrix means the matrix is a complex symmetric matrix. Apart from that, if it is a WSS process, it will have uh, all the uh, components of the matrix defined uh, by its first row. So all the components of the matrix will be kind of defined by all the elements in the first row. Also, we have to know that if it is a WSS process, the eigenvalues of the matrix will be either 0 or above 0, which means that the matrix will be a positive semi-definite matrix. If it is a positive semi-definite matrix, we know that the eigenvalues of the matrix will be either 0 or above 0. So that is one of the properties of that WSS processes autocorrelation matrix. So, so if you have a certain matrix, you can find eigenvalues of that matrix. So the eigenvalues of that matrix will be uh, either 0 or above 0 for a positive semi-definite matrix. So for a WSS process, this condition will be valid. You have to find the eigenvalues and you have to find whether it's 0 or above 0. If it is that, then we can say that whatever the process that we are considering is a WSS process. So if you are given a matrix, you can be asked to find whether it's a WSS process. So you can do that by finding the eigenvalues and you can check them to see whether they are equal to 0 or above 0. If that is the case, that means that process is a WSS process. So if you are given a matrix, you need to find the eigenvalues in a certain manner. So basically, you'll be using the determinant of the matrix to find the eigenvalues. So I think if you have a certain matrix, for example, you can find the determinant by considering the determinants in specific manner. So if you have a like let's say if the autocorrelation matrix is given as having values of maybe 2 and minus 2, and then 2 5 minus 4 minus 2 minus 4 5. If you are asked to find the eigenvalues of this, which is required for us to find out whether it's positive semi-definite or not, we need to find the determinant of the components that are in here in a certain manner. So I will try to show the dimensions you have to consider here. So in here you need to first find the determinant of this component, which is 2. So after that you find the determinant of 4 by 4 matrix inside this matrix. Then after that you have to find the determinant of the entire matrix, which is 3 by 3 matrix. So in here, actually, this is a matrix. So I'm going to denote it like that. When you're finding the determinants, you will be putting this sign. And the first eigenvalue is basically 2, which is above 0. And then, so we will denote this as lambda 1. Lambda 2 is the determinant of the next, uh, you know, portion of the matrix. So which is given by 2, 2, 2, 5. So we take the determinant in here and we will be seeing that this determinant will be equal to 10 minus 4, right? So this is 6. This is also above 0. And then if you find the lambda 3, it will be the determinant of the entire matrix. If you find it, you will be also able to see the eigenvalues of that matrix either above 0 or below 0. Depending on that, let's say if it is above 0, then you can say that this is a positive semi-definite to positive definite matrix. So positive semi-definite means that that eigenvalues can either be equal to 0 or above 0. So if they are all above 0, you can also say that this is a positive definite matrix. So this is a positive definite matrix. So anyway, if the eigenvalues are above 0, that means that the matrix is a positive, I mean, definite or semi-definite, which actually implies that the process is a WSS process and that its features are kind of stable. So do you have any questions? So if you haven't discussed about the positive definite matrices in your previous classes, maybe you can find out about that further by referring the sources related to mathematics, right? So, what I need you to know is that if it is if you can find the eigenvalues, and if the eigenvalues are non-negative, uh, then you can say that it is a positive semi-definite matrix. So also for a positive semi-definite matrix to be considered as that, the eigenvalues should be non-negative and also the matrix should be symmetric. So you need to check both these properties. So earlier also we mentioned about the symmetric, so that is why I did not mention in here. However, if you are considering only the positive semi-definite matrices definitions, a matrix becomes this positive semi-definite only if it is symmetric and also its eigenvalues are non-negative. So you need to check the eigenvalues and its symmetric nature to find out whether it's and to determine whether it's a semi-definite matrix. So I think up to that point we have discussed about the cross correlation matrix. So I think by now, if you are given a kind of a information, I think you will be able to form autocorrelation matrix based on that information. So I would like now to discuss about the linear time invariant systems. And before that, if you have any questions, you can ask. Also, if you are wondering, that we are hoping to have the exams on the first 2 weeks of March. So I think you have one more month, this month and another month. Right? So in order to get the ready for the exam. So the concept we talked about the autocorrelation matrix is important for us to discuss about the LTI systems. So when we are discussing about LTI systems, the concepts of autocorrelation, concepts of cross correlation will come again. So because of that, I think it's good that we discussed that earlier. So LTI systems, anyway, we can discuss under time domain and frequency domain. I mean domains. So time domain and frequency domain. I think we discussed earlier also about the time domain and how we can define the output of a signal, output of a system using the convolution between the impulse response and the input signal xn. So this is the convolution operation in here, which is a costly operation, and this can be considered, and we can find the impulse response by using an impulse, and we can find the transfer function. When you're observing the frequency domain, you need to observe the frequency domain due to many reasons, and you need to find out the frequency components of the signal, the behavior of the signal in terms of frequency domain, and about the existence of harmonics and existence of noise. Those things you can find using frequency domain. So when you are doing that, you have to know the Fourier transform of the signal, and also other transforms are also kind of used frequently in identifying the signal components in the frequency domain. So it could be like Laplace transforms, Z transforms. Those things are also coming into play when you're analyzing the signal in the frequency domain. So the easiest way for us to identify the signal will be maybe in the frequency domain, and it will be can be defined like this. Output of a certain signal in the frequency domain is a multiplication of the transfer function with the input signal's frequency domain signal. So this frequency domain analysis has also many advantages because of its reduced complexity, and therefore we tend to use Fourier transform or Laplace transform or Z transform to find out the system characteristics. If you want to find out the statistics of the LTI system, we have to find different statistics such as the autocorrelation that I just mentioned. When we are trying to find those things, we can either use Matlab or we can use numerical analysis for the calculations. So we can do both using Matlab, both theoretical, numerical calculations. So before going further, I will try to explain a situation where we need the correlation and autocorrelation, cross-correlation values in our study, and what is the application of those statistics in these kind of systems. So when we have a system where we have some kind of input signal xn, where we want to find, let's say we have a output yn, and then we want to find out the cross correlation between two signals. So let's say in here let's say there's the impulse response hn. Then in here we have the xn signal again, and we can try to find the cross correlation between the yn and the xn. So the cross correlation value we can find, and we can denote that as yx, ryx. So this one is a correlation value. R is the correlation value, and it is between y and x, or the output input autocorrelation. Sorry, cross correlation. If there are two different signals in play, we call that cross correlation. Or if we consider the same signal only, we call that autocorrelation. So this is the different signals y and x that we are considering. So we will be calling that cross correlation. So the output cross correlation will be between output y and input x. So in here we can find the cross correlation value. So using that, we can find out whether there is some kind of a similarity between yn and xn signals. So autocorrelation or cross correlation, this correlation function finds out the similarity between two signals. In here, the output will give us the correlation between xn and yn. So the cross correlation operation will happen in here. This is doing cross correlation. So this cross correlation is used in situations where we want to reduce the difference between yn and xn, right? So as I said before, in situations where we are using a phone call, when we are transmitting a signal from one device to another device, the receiving device will get a signal called yn. However, it wants to decode the xn, or it wants to decode back to xn, or else it want to find out xn. So if we want to do that, it needs to identify the difference between that y signal and the xn signal. So that difference can be found by using cross correlation functions. We can find out how similar the output received signal with the original transmitted signal. So RYX is useful for us to identify that there's some similarity between the two signals and whether there's a huge error or gap between the two signals. If you want to, like, for example, I mean, going ahead of the other example that I mentioned, we can also use these kind of, you know, these kind of systems to filter out noise in a received signal, and we can obtain the original signal by filtering out the noise, and that noise can be filtered out by using this cross correlation function, which gives us how much of similarity is there between the input signal and the output signal. So by checking those things, we can actually create a filter that will remove all the unwanted signals such that the input signal is equal or very similar to the output signal of the filter, right? So the for filter operations, filter applications, this concept of cross correlation is very important, because the cross correlation gives us the like information about how, I mean, similar two signals are. We can find the similarity of two signals using this cross correlation functions. So when we want to find out RYX, we can find that by using the mathematical equations that we just derived. So for RXX, we already defined, but for RYX, we will just define. The only difference in here is that the two different signals are considered X and Y. So when we consider this setup, this is one setup that could be taken as example where we need the cross correlation, and cross correlation examples are also very useful, as I said, in filtering operations. So when we consider a situation where we give a white noise as input, let's say we are giving white noise as the input, our input will be having an autocorrelation value of um, autocorrelation value of n naught over 2 delta L, right? We just learn about the white noise having the autocorrelation of n naught over 2 delta L for white noise, which is having a power spectral density of n naught over 2. So for that case, we will be able to find the um, we will be able to find the cross correlation once we have the yn output. So by doing so, we can find the um, cross correlation in here once we have yn and we already know xn. So um, so we can denote in this situation, we can denote um, we can denote that rxxl is n naught over 2. delta L. Right, so this is actually for a like a specific case. This is for a specific case where the white noise of NO2 is considered. So if we can consider like a general case, we can also consider that we are giving an impulse of or I mean we are giving a white noise of having autocorrelation delta L. So in order to actually simplify the calculations, we can consider for the moment that autocorrelation value is uh, delta L. We can consider this and not two factor later. We will first consider the case where autocorrelation value at the input is delta L. So this is uh, the uh, input that we are going to consider, and the input will have autocorrelation value of delta L. So which will be something like we'll be having a spike at the L equals 0, a spike of 1. The amplitude of this will be 1 in here. At L equals 0, the amplitude of the delta function will be 1. So in here, the autocorrelation value will be 1 at L equals 0. So when we are defining the output RYY is the autocorrelation value of the Y signal with its own signal. So autocorrelation between Y with its own signal is given as RYY L, which gives the time gap between 2 points, and this can be defined as the convolution between HL and XRXX L. So this is kind of the relationship between autocorrelation values between the input and output. Autocorrelation of the input is equal to the autocorrelation of the output and into the HL. So this is the output autocorrelation. So this is how normally the autocorrelation relationship is defined. There are other definitions also similar to this. We can denote autocorrelation between X and Y using uh, using a conjugate of the HL into convolution with the RXXL. So, so this is another relationship that we can obtain between the autocorrelation of XY, and it will be equal to this. So when you consider this RYX, it will be something similar, but there will be some differences such as HL convolution RXXL. So which means that if you consider autocorrelation, the order in here that you put, order of X and Y that you put, affects the autocorrelation value or cross correlation value. So these are actually cross correlation values. So the cross correlation value depends on the order that you are defining the X and Y. Let's say you are defining it as X and Y, then or else you can define it as Y and X. So if you are defining in a certain manner, the output of impact of that will also be different. So the HL will be convoluted with RXX if this equation is considered. So there will the expression will be like this. So if you are considering the RXY, so in here sorry, there should be a minus L as well. So in here the relationship is there, but it's different in its impact. So RXY is equal to the H star minus L convolution RXXL. So the reason being that this is the relationship. I mean, the second relationship is the one which has the relationship defined using the convolution directly between the impulse response and the RXX. If you have the RXY considered, you will have to consider the kind of the inverse of this impulse response in here. So it's kind of the inverse, and that impact should be shown in here using this conjugate signs and minus signs. So so regarding the cross correlation or functions, that is related to that. If you also extend the equations, there's another equation that defines the relationship between the autocorrelation value of Y with the autocorrelation value of X. So you can write that autocorrelation using the this expression as well, where you define the autocorrelation value using autocorrelation of the impulse response also. So earlier we defined the RYY earlier in like this. So I think in here it should be I have to make correction in here. It should be RHH into convolution into RXX. In here, this autocorrelation value of the impulse response. So autocorrelation value of the impulse response is convoluted with the autocorrelation of the input signal, and that will give the autocorrelation of the output signal. So that is what I was trying to get in here. So that is the relationship that you have to keep in mind. So the this in here you take the conjugate of the H or impulse response and take the convolution with the impulse response. So you take the convolution with the HL and then again convolution with the autocorrelation value of between X, autocorrelation of X. So this will give the relationship. So this is same as what we have defined in here. So these are same. So this is the time domain representation of the relationships between input and output when you consider the correlation properties. If you are considering in the frequency domain, these can be represented using the frequency components or the frequency domain signals. So you are representing them using the frequency domain. That can be done using power spectral densities as well. So when you're going to the frequency domain, you can uh, first of all you can denote directly using direct Fourier components, where you define the output of the system as YF and denote the transfer function of the system as HF and input signal as XF. If you want to denote all of them uh, in the frequency domain further, can denote that using the power spectral density values, which can be denoted like this. So e to the j omega. So e to the j omega can be used to denote the frequency content of the signal. So omega is denoting the 2 pi f, right? So omega is denoting the angular frequency. So omega is the angular frequency and it can be related to the frequency. So it is related to the frequency as omega equals 2 pi f. So omega is equal to 2 pi f. So omega and f are interrelated. So when you are defining signals in the frequency domain, you can either define it using frequency directly f, or you can denote them using e to the j omega. So however, these are not equal. F and e j omega are not directly equal, but f and omega equal or related using this expression. This is the relationship between frequency and omega. So if you are going to denote the relationships using ej omega, can be done in this manner. So the power spectral density of the signals, when you take the power spectral density of the X signal, and then you take the power spectral density of this transfer function, you can take the relationship like this. So there will be multiplication in here. So similarly, you can give some expressions for all these signals. So I don't want you to remember this. I will give you, if I want you to use these equations, I will give you that in the exam. There will be some equations that I want you to remember, but this equation I don't want you to remember. So using these equations, you can find the impulse response if needed of the system. So using power spectral density values that you can measure from a certain equipment, you can find the transfer function of the system. You can find the transfer function using power spectral density values at the input and the output. So this final equation, of course, can be easily identified and understood. In here, you can see that this is the output power, this is the input power. So they are related using this transfer function of the system. So once you know the transfer function, you can find the power out and or any other variable that you don't know. So that is basically regarding the frequency domain outputs. So there are some relationships in the frequency domain as well. So all these frequency domain calculations can be done using Fourier transform, Z transform, a Laplace transform likewise. So depending on the different application, we need to select the type of transform that we would like to do. So we'll be converting our signal from time domain to frequency domain. So do you have any questions? So so if we want to calculate these equations on our own, we can also do that uh, using the definitions of the autocorrelation and cross correlation, for example. So we will take, for example, this equation that we have uh, defined earlier, which is regarding cross correlation. So I think we have discussed about autocorrelation multiple times. So we will therefore we can actually define the cross correlation value. So the cross correlation value we can define uh, by taking the cross correlation between two signals like y and x. The cross correlation between two signals y of n and uh, with the um, so the cross correlation value between y of n and x conjugate of n minus L will give us the autocorrelation, cross correlation between the two signals. So the the 2 points that we are considering are coming from the Y signal and the X signal. The cross correlation we will basically consider here um, by considering the uh, by considering 2 points in the two signals, which is n and n minus L. So we are going to consider 2 points which are having a time gap of L. So in here we have a time gap of L that we are considering. So because of that, the time indexes in here will be N and N minus L. Also, we will be considering the complex conjugate of the signal, mainly because if the signal is a complex signal, we have to consider the complex conjugate of the signal when we are considering the cross correlation or even autocorrelation. Since we only considered about the real signal so far, we did not put this conjugate sign. But in general, if you are finding the autocorrelation between two signals, let's say RXX L, between two signals of gap between them is L, then we have to consider this conjugate of that same signal, and then we have to take the multiplication. So we need to consider this conjugate of the signal just in case to consider the complex signals that we are going to compare it with. So the complexity or the complex nature of the signal also must be considered when we are finding the autocorrelation value or the cross correlation values. So when we have this equation, now we have to find out the output of this. So the yn is defined as um, the convolution between hn and xn. So the convolution we can define as a summation of the k equals minus infinity to plus infinity, and then multiplication of hk with the xn minus k. So minus infinity to plus infinity hk into xn minus k. So this will give us the yn component. Then you will have to multiply this with the conjugate of the x, which is defined by this. So once you consider all these things, we can see that if xn is a random signal, then xn is a varying variable, some kind of a variable. So hk, of course, we assume that we know that by using the impulse response of the system. So hk, we can take it out as a deterministic signal. So since it is a deterministic signal, we are going to take the hk out, and then we are going to put the expectation operation only on the random signals that we are considering. So expectation operation on xn minus k into x conjugate n minus l. Then expectation will be conducted only on those random signals. So the summation of k equals minus infinity to plus infinity hk will be remaining outside. So once you take the expectation of these two x values, x components, you can say that this is the autocorrelation value between two signals with a gap between L minus K. When we are subtracting these two terms, you will get L minus K. The gap between the 2 points is L minus K. And that will be multiplied with HK with this summation. K equals minus infinity to plus infinity. So this is how you obtain the final outcome of this ryx. This can further be written as the convolution between hl convolution into rxx l, because there's a gap of l basically between these two signals. So this will be the final outcome for the ryx of gap l. So ryx gap of L you will define, and that will be equal to the convolution between the two signals. Right? So this is the relationship that we have obtained. So similarly, we can obtain relationships like this for the rest of the equations that I mentioned in here. Right? So although I said that these equations you don't have to remember, these equations you don't have to remember, but these correlation functions and the equations related to them, I think you might need to remember these ones. These will be used every time that we'll be doing some filtering, or when we are doing some system based, like calculations between input output. These autocorrelation values and cross correlation values will be useful. So because of that, these equations you need to know, these equations: cross correlation, autocorrelation equation. So for the other, I mean, this is one computation of the cross correlation between y and x. Similarly, we can reduce the equations of the other relationships also. So if we consider, so this is all, this is considered as the correlation between output input. So this is known as the correlation of output input. If we want to find the correlation of output only, we call this output correlation. So that one we can also compute. So the expectation of y, so we can take the expectation of y with another y point where the gap is L. That will be the definition of autocorrelation with a gap L. So when we expand it, you can write like this. Yn can be written like this, where the convolution between h and x has been taken. This is coming by definition for the yn, which is the convolution between hn and xn. Then this will remain the same. Once you get to this point, you can take hk out as I did before and only leave x n minus k and y conjugate n minus l. So this can be further written as rxy, and the uh, so the uh, rxy, and then inside brackets l minus k. So since this is a product in here, now we can denote this as convolution between h, l, and uh, autocorrelation of l. I mean, the gap between these is l. So I'm going to write autocorrelation of l. So in here, I have to denote the convolution sign. In here, it should be convolution sign because in this previous step, it is the convolution operation that we are doing. So with this, we can derive the autocorrelation of the output. Maybe you might need to know how to calculate this autocorrelation in this manner so that you can derive these equations. So you might not need to remember them, but you might need to derive these equations in this form. when we have LTI system with the impulse response HL, we can denote the HL and we can denote the relationship of autocorrelation, cross correlation values by we can denote these relationships using this diagram. You can denote them using, for example, if you have an input in here and the autocorrelation value of the input is it can be related to the system's output correlation or output autocorrelation like this. So when we have this kind of system, the these are all related to one another. So this is the input to the system, and this is the where the output comes of out of the system. So then we have the not auto correlation, cross correlation. We have this RYXL in here. So we can put RYXL in here, and then we can write the equations that we derived earlier using this diagram only. So earlier we wrote this RYX equals the HL convolution RXXL. So that can be written using this diagram. RYXL is equal to the HL into RXXL. So using these three components, you can see uh, this is the output, this is the transfer function, and this is the input. After that, you can do the same for other relationships and obtaining other relationships as well. However, if you want to obtain the relationship where we have the RXY, you need to convert this um, direction, right? So currently we are having this in this direction. RXX is equal to HL into RYX. However, if you want RXY, you need to convert the other components or based on that. So what we do is basically convert this impulse response in such a way that it is uh, it is converted in totally inverse, and we can we can write the relationship like this between the input correlation and the uh, output cross correlation like this. So this is the relationship that we obtained earlier. So this is a relationship we can obtain from the above diagram, but we need to invert the impulse response and multiply that with the RXX to obtain RXY. So finally, we can also write the RYY of L using the autocorrelation of the impulse response into the convolution with the RXXL. So this is the relationship that we can write also for the entire system. So this is the input, this is the output autocorrelation, and this RHH denotes the autocorrelation of the impulse response. So inside this box, we have the transfer function area. Whatever the area that we use to find the transfer function, we have it inside this box. The like other components are basically inputs and outputs of the system. So with that diagram, we can quickly, I think, identify how the relationships are like they are between two parameters in the system. So another thing about the LTI system is power of the signal. So this is a new thing. So the power of the system's signals can be denoted using the value of R, RXX0, or RYY0 will give the output power of the system. So output power of the system will be given by the RYY0. So RYY0 gives the output power of the system. So input power of the system can be found by the RXX0. So whenever you find the RXX value and find the 0 point, you can find some energy of the system. So our output power of the system is given by RYY0, and RYY0 is also equal to E, or expectation of Yn absolute squared. So RYY0 is given by this expectation of Yn squared, which gives the power of the system, or the output power of the system. Right? So expectation of this value gives the output power of the system. So if you know the values of Yn, you can find this magnitudes and you can find the expectation value. Numerically, when you try to find the equation, it is having some complex expression. So therefore, finding the power of a certain system is a little bit complex in that situation. Little bit complex. And then if you want to find the PDF of the output of PDF of the Y, which is the output of the system, you need to find the probability density function or a probability mass function. However, that is also generally a complex procedure, and therefore it's like unable to get a very beautiful function to calculate the PDF of the output Y, or a PDF of the random process, which is the output of a system. It's difficult, a little bit complex, and therefore we try to use the other statistics and get the necessary observances about the systems. So if you want to find the cross correlation or correlation between two signals, you can either use Matlab or you can use numerical calculations. If you are doing in Matlab, I will explain how the process can be done step by step. Then you can implement it in the Matlab. So if you have any questions, can you let me know? Do you have any questions? Any questions? When we learned about these things, we also discussed that we need the Fourier transform and the Fourier domain analysis of the signals. So in order to do that, we have to also understand about the Fourier series and Fourier transform. So there are many kind of transforms that are available with the Fourier domain or frequency domain. So when we consider uh, frequency domain of a signal and denoting that in the frequency domain, we can denote that using different kind of transforms, Fourier transforms, then Laplace transforms, Z transforms. So when we have all these transforms, we have to use the specific transform based on our application and based on the type of the signal that we have to transform. So first, let's actually look at the Fourier transform, and then we will get into Laplace and Z transforms. So Fourier transform, when we consider that, it also has many variations. So the Fourier transform can be divided into, continuous time Fourier transforms and discrete time Fourier transforms. So before that, Fourier also can be separated into Fourier series and Fourier transforms. So Fourier series and Fourier transform are two, like two sides of Fourier analysis. So Fourier series is used to analyze the periodic signals. Periodic signals. Periodic signals are signals which are periodic in nature, which means that it's repeating its pattern with each period of capital T. It's having a period, if it is having a period of capital T, then the signal's amplitude will be same when you reach a capital T time. When you reach a capital T shift, then you will see the same amplitude occurring. In that case, the periodic signals are defined. If you have the aperiodic signals or not symmetric signals, aperiodic means they are not symmetrical. So in periodic signals, you can see some kind of a pattern. In here, in the aperiodic signals, you don't see some kind of a periodic pattern. So aperiodic signals, for them, transform is defined. Fourier transform is defined for the aperiodic signals. Also, I mean, when you consider about the Fourier transform is basically used to find the components of the frequency in the signal. So frequency components of the signal. So when we consider about the frequency components, there are multiple, components that can be there in the signal. So there can be the fundamental frequency component, and there can be the other frequency components, such as the harmonics, which are something that we don't want to have in our system. So when we consider the frequency components, they can be either fundamental frequency component, or it could also belong to harmonic frequency component, or harmonic high frequency or unwanted frequency components. So when we are doing these transforms, we can see how these harmonics are defined and how these harmonics are distributed over the frequency domain. So when we discuss about further about the Fourier transforms and Fourier series, we can also define these uh, transforms in a different manner. So when we define the transforms, we can also again divide them, the transforms, according to the input signals uh, type of the input signal. So if you are considering, let's say we are considering Fourier uh, cases only, like Fourier transforms and Fourier series, then you can consider them either in continuous time domain or discrete time domain. So we can consider them as either discrete domain or continuous domain signals. So earlier I said about Fourier as to which type of Fourier transform can be done based on the nature of the signal. So this is based on whether the Fourier, whether the signal is periodic or not periodic. So based on that, you select the type of transformation you are going to do. So in this part, it is like you're considering the input signal's nature, and you are determining what is the best method to transform that signal into a frequency domain signal. So when we consider the Fourier transforms or Fourier series, we can consider the signals which are in continuous time domain, and we can consider signals which are in the discrete time domain. So if you are considering the continuous time domain signals, you can do transforms in the continuous time domain. So it could be like continuous time Fourier series and then Fourier transform. Also, you can consider for the discrete time also the same thing, Fourier series and transform. The only difference in here is that the input signal that we are considering, or the time domain signal that we are considering, is in the discrete time. So the time signal is in discrete time instances. In here, the continuous time means that time signal has continuous time samples. So in general, in the reality or in the practicality, we will be sampling the time signal. So sampling of the time signal will result in discrete signals. So we will be sampling the time signals or continuous time signal, and then we will be using that samples to make some analysis about the system. So once we are getting the samples, that signal that we are considering will be a discrete signal. So for discrete signals, we will be doing discrete time Fourier transform or Fourier series conversions. So under discrete time, we will be having again discrete time Fourier series, which is we call as DTFS, or else discrete Fourier transforms, right? So this is Fourier series. So discrete time Fourier so discrete time Fourier series, discrete time Fourier transform can be done. So this is discrete time Fourier series. So these are some transforms that we can do. So when we are working in the real world, as I said before, we might use DFT operation more than these two operations. So these are operations which are considering infinite number of samples. So infinite number of samples, if you are considering, then you will be using this DTFS and DTFT, which corresponds to discrete Fourier series and discrete time Fourier transform. So these are actually theoretical concepts where we consider infinite number of samples. So theoretical concepts. However, when we are doing the real-time concepts, then we have to use a finite-sized signal. So finite-sized signals are considered and converted into Fourier transform using discrete Fourier transform. So this is a finite sized, uh, you know, uh, signal or transformation of the finite sized samples. Finite sized samples or signals. So finite size signals are the ones that are available in our normal, our practical systems, where we collect some data regarding some kind of signal for a finite sized time interval. We are not going to infinitely record some kind of data. So we only have the data samples for a finite time duration. So this finite time duration is therefore is have to be analyzed, and we have to analyze the system based on this received data. We cannot do anything about the lost or unavailable data. So other data will be zero actually. Only the T1 time duration will have some samples. So when we have these samples in this time duration, we have to use this and assume that the rest of the signal is also there. And then we have to do the transform. That is what is done normally using the simulators, Matlab or some other simulators like Python. So what we do there is that basically find the Fourier transform of the available components by considering that uh, the samples values are repeating in a periodic manner. So the main idea is that for finite number of samples, where we only have a finite number of samples, we do the discrete Fourier transform. If we have another transform type, which is a fast Fourier transform, it's basically an like a simple way of calculating the discrete Fourier transform. Simple way of calculating the DFT uh, using some kind of mathematical manipulations. So simple way of calculating the DFT is given by FFT. So the calculation can be done uh, using simple manner or with less calculations than DFT. So uh, so basically that is regarding the transform type. So this is known as fast Fourier transform. So do you have any questions up to this point? In this class, we'll be basically looking at this DFT, FFT operations. As you might understand, the continuous time Fourier series and continuous time analysis and computing the Fourier series and transforms is not that practical, because although we have this continuous time signals in the environment, we as limited memory sources with limited resources, we can only store a limited amount of data in our devices, or else in any kind of embedded system or something like that. So if we don't have any space to store all the information, we can't take continuous time signals. So if it is the case, since we are having this discrete time frequency transformations, we can use those to find the transform of those signals. So anyway, like once you get the uh, discrete Fourier transform of the finite sample, you can find the Fourier transform of that signal. So in the finite sample size, you will be using DFT. With that, I think I will discuss uh, about the FFT implementation in the Matlab also. So if you have any questions related to this part, you can let me know. Also, this is a like a table of how the Fourier transforms are defined. So if you have a time domain signal, or if you have a time domain signal, the Fourier transform is basically uh, saying that the transform is basically saying that any time domain signal can be defined as a combination of sinusoids, a combination of sinusoidal signals. So the basic idea behind the Fourier transform is that. So if you can try to understand that further, you can see that in here this integration has happened between minus infinity to plus infinity, and then that integration happened between exponential functions in here. So these exponential functions are representing some sinusoid included sinusoid, and these sinusoids can be manipulated in ways such that you can represent a sinusoid using these exponentials. So anyway, like by the combination of sinusoids, you can show any time domain signal, right? You can combine multiple sinusoids and you can show a time domain signal. So that concept is what Fourier has introduced uh, as his theorem, Fourier transforms and Fourier series. So he is the first person to tell that any signal can be represented as a combination of sinusoid signals. So if you want to find the Fourier transform of a signal which we know in the time domain, you can use this equation in here. So if you know the time domain signal gt, you can take the e to the minus j 2 pi ft dt to find the gf, or the Fourier transform of that signal, time domain signal. So this is basically the definition of the Fourier transform. So maybe you can try to keep this in your mind, these definitions, basic concept and the definition you can keep in mind. So uh, you can refer the Fourier transforms of different types of signals as well. I will share this page in the LMS for you to see, but I'm not going to ask you to find the Fourier transform of definite single functions. But there could be some places where you might need like some understanding about the Fourier transform of like basic signals such as the delta function, the other functions which are very trivial or which are very well known. So you might need to know the Fourier transform of some of the special functions, and also the basic way of finding the Fourier transform without any problem using this main concept. So as I said before, this Fourier transform is used to denote any signal in the time domain as a combination of multiple sinusoid signals. So do you have any questions?
Madam, excuse me, madam, we can't hear sound any.
Okay, can you hear me?
Uh, Now okay, madam.
Yeah. Okay. So basically the definition is this. So I was writing it down. So thank you for telling that. So I think you just need to know this definition about the Fourier transform. So any time domain signal GT can be represented as a combination of sinusoids, um, and that can be represented using this equation. So the combination of sinusoids can be represented using this integration. So basically sinusoids can be formed using this e to the j 2 pi ft expressions. So using Euler's formula, you can form sinusoids using exponential functions. So if I consider the Euler's formula, I can denote the sinusoid using Euler's formula. So if you consider uh, sinusoids, or sinusoids include cosines as well. So I consider the cosine signal, which is having a very like a positive uh, expression for all the components. I mean, cosine signal can be defined using e to the j 2 pi f t plus e to the minus j 2 pi f t. So in here, the sign is plus for the cosine. That's what I mean by plus. So anyway, like Euler's formula can be like this. Using Euler's formula, you can find the uh, you can define the definition for a cosine or sinusoid signal using exponential functions. So exponential functions um, can be used to form a sinusoid signal. So similarly, what that's why we have e to the j 2 pi ft expressions in this Fourier transform definition. So in the Fourier transform definition, we say that we need a combination of sinusoids, and we can use that combination of sinusoids to denote a time domain signal. Any kind of time domain signal can be denoted using a combination of sinusoids. So this is the concept that was, proposed by an engineer who was in France, and who, presented this idea. Fourier, his name is Fourier, and he has presented this idea. So this idea has been presented in front of other, great scientists such as Laplace and Lagrange, likewise. So those concepts were already there once this Fourier transform was introduced. However, this introduction has been done by that engineer, and this has been like a new concept that has been introduced into the world at that time. And currently, we use this Fourier transform in almost a lot of all the like signal processing activities. And in kind of places where we want to observe the Fourier domain and Fourier domain of the signal. So with that, I think I will discuss about the Fourier transform further, maybe in the next session. So now I will give a small quiz for you to attempt, and then I will discuss about some Matlab simulations that you can do in the Matlab to find the Fourier transforms. So do you have any questions? So in today's class, we discussed something related to the LTI systems and the Fourier transforms. However, I still have to discuss about the estimation techniques, which are including mean square estimation and the minimum mean square estimation. Okay, MMSC and MSC I have to discuss also. So minimum mean squared error is minimum defined by MMSC term, and it's also one of the most used estimation techniques, especially in communication field and also in other fields where you want to optimize the error uh, of the optimize the error and reduce the error of the received signal, error of the received measured signal. So this quiz will be regarding what we discussed. So there's only 5 questions in here, so I will share it with you. So please join into this quiz.
Could you share the link?
So you can join using this pin as well. So I mean,
Okay.
you can. I will start then. So the correct answer is mean squared error. So I think all of you got most of you got the correct answer. So mean of the error we are finding in the mean squared error. We are taking the not only the minimum. We are not considering any minimums. We are going to take the average of the error that we see along the entire process, along the entire signal samples that we considered, and we are taking the mean value of all the errors that we have. The correct answer is minimum mean squared error, which is the another extension of the mean squared error, which um, optimizes the error and find the possible location where we can obtain the minimum error in the entire system. So it's a more advanced version of the mean squared error technique. So the range of frequencies are given by the word spectrum. So spectrum means like all the different frequencies available in the signal. And you can use the spectrogram to watch that. Spectrograms are used to observe the frequency components inside the entire frequency range of the signal. So all the frequencies are given in the spectrum. So the correct answer is you can show a continuous signal using a infinite series of sinusoids. So infinite comes because we are considering the integration from minus infinity to plus infinity, right? So infinite means you're considering the infinite range. So infinite range possible, and defining the combination of sinusoids through that infinite range of frequencies. So a continuous signal you can denote using combination of sinusoids. The combination of sinusoids, the number of sinusoids can be infinite. Okay. So this is wrong, mainly because Fourier series is defined for periodic signals and not for aperiodic signals. Aperiodic means not periodic. It's a term used for denoting not periodic signals in the in maths and signal processing. So aperiodic is wrong. So Fourier transform is used for aperiodic signals. So this is statement is totally opposite. So therefore it is wrong. I will publish these results and I will put them in the LMS. So I think that's for today. So when you're giving the names, I think you should give all the registration numbers so that I can put the marks under each of your registration number. So thank you for participating in that. So now I think I will go to the Matlab. So when we consider the Fourier past Fourier transforms, we can do that directly using FFT command in the Matlab. So this is one example of doing that. You can create a signal. You can try to find the past Fourier transform output of the signal. So what basically it does is that it identifies the frequency component of the signal. If you have a sinusoidal signal which has a certain one frequency, let's say it's having a 3 Hz frequency, then the FFT should show the frequency component and its amplitude in that 3 Hz frequency. So in this code, we we have defined the sampling frequency of the signal as 40 Hertz, time as 1 over sampling frequency. So these sampling frequencies are used to plot the signal. So when you're plotting, these points will be defined, the points of plotting will be defined based on the sampling frequency. Also, the capital N means like the number of samples that we are considering for the signals. So as I said, like FFT or DFT, we are considering the samples to be finite sized. The number of sample size will be finite size. So we have to define the sample size when we are working with FFT, DFT calculations. So sample size will be 40. And then that is the sample size we will be asking the computer to compute the FFT of. And then we consider time vector. So also we consider, we give them the signal, the input signal in the time domain. So in here we are considering a sinusoidal signal with a frequency of 2 pi 3 t, which means the frequency will be 3 Hertz. So it's given in this 2 pi f t format. So 3 Hertz signal we are considering. So this one we can plot using this code. So once you run it, you will be able to see the output. So the output will be coming in this manner. So since this is a live script, it will already, generate the outputs whenever I run. Without running even, it will give the output. So this is the output you get for the first part where we plot the input signal. So these points are defined by the points that we have considered. So we are considering time points using this time vector. So based on that time vectors points, this blue points will be plotted in this. Then we have something called one-sided FFT. So why do we say one-sided FFT? So mainly because FFT can be defined in both sides, so in both the positive and negative sides. So FFT will be denoted in two sides which contain both positive and negative frequencies. When we are working with the frequency domains, positive and negative frequencies are something that we cannot, ignore. We have to ignore. We cannot ignore the negative frequencies. The negative frequencies are there to represent the direction of the uh, vector that defines the signals phase and the signals uh, uh, what do you call that, the polar behavior of the signals components. So based on that polar plot of the signal and based on that polar vector that we have in the signals, the same time domain signal can be represented using negative frequencies also. So negative means like the frequency magnitude, though the magnitude of the frequency is same, but negative is defining something like a direction of the signals, change of phase, and so on. So anyway, so one-sided FFT will be giving you the positive side of the frequencies or the positive frequencies of the FFT. So one-sided FFT will give the positive frequencies of the FFT. So when you want to find the fast Fourier transform, you basically give the input signal and then you give the command FFT. So since this is a finite size signal, the output will give the FFT values as also finite signals. So there will be finite number of signals as the output. Then you can plot the output for the region that you prefer. So in here, they have taken the output over the N0/2 region, which is the kind of one side of the FFT. So basically this is how they have taken the one-sided FFT. So after doing that, they have plotted with the frequency of the signal. So that is possible. So the frequency specific frequencies that are considered are considered in this time or frequency instances, where we consider the frequency instances from k equals 0 to N0/2, and based on that we define each of the unit frequencies that we will be considering in that range. So the total number of time total number of length points we are considering are defined by n, and so based on that we consider the unit frequency values using the frequency vector. So after doing that, we can compute this one and we can find the plot. So this plot will be coming like this, where you find that there's a frequency component at this exact 3 Hertz location. So FFT gives us the frequency component of the sinusoid signal. So sinusoid signal has a 3 Hertz frequency that can be seen using the FFT plot. So so this is how you can see that FFT. When you consider other signals also, you can do FFT for a delta signal, which has a spike in the at the origin. You can find the FFT of a delta signal using this kind of a command. So delta signal will have a time domain signal like this, that at the time domain, its value at the origin or at one location, at a certain location will be 1. So once you compute the FFT, you have to compute the FFT by defining the number of samples also. So for defining number of samples, you can give the signal and then comma, you can give the number of finite samples that you are interested in considering. And then you can compute this FFT like that. So for FFT, you need to define the number of samples that you are considering of the signal. So the signal, otherwise the signal will be infinite, since we have only given the value of the signal at a certain particular frequency or a certain time instance. The rest of the time instances, the amplitude of the signal in those other instances are not known to the simulation. So in order to define the number of specific time samples that the software should consider, you give the number of samples to consider. In here, it's n equals 8. So after doing that, you can run this and you will get a plot like this, which shows you that the amplitude of the Fourier transform of the delta signal is a constant value at 1. So you know that delta signal has a magnitude of 1 over all the frequencies possible. So this is what it is showing. If you want to find the sinusoidal signals again, if you want, again, there's another implementation of that. So if you know the certain frequency components of a, if you plot the sinusoidal frequency, you can find that the FFT of that signal has frequency components. So in here, there are two main frequencies where it has two main points of frequency where it has certain signal or a certain amplitude. So at 4 Hertz and at 28 Hertz, it has certain amplitude. So this sinusoid signal has two frequency components, therefore, at those frequencies. So it is not an exact pure sinusoid, it is a combination of two sinusoids. So based on that, the frequency components of the signal will vary. So I think with that, I will end today's class. So if you have any questions, you can let me know. Do you have any questions? I will share all the codes that I'm discussing in this class with you. So don't worry about that. I will share those with you. So any questions?
Good morning, ma'am, and happy New Year.
Yeah, yes.
I remember you were telling end of the classes will be 27th of January.
Yes, so actually there were 2 weeks of holiday that I gave to the students. So because of that, we have to do 2 weeks of additional lectures next month, February, first week and second week. And then we will have a study leave period. So is that what you're asking?
No, I'm asking whether we can be delayed with the submission of the first assignment.
First assignment.
It says 27th of January, and I remember you were telling you can submit it at the end of the lectures. Just asking, we can submit it by 27th.
I think you had enough time, I think, because I will be giving some more assignments. So maybe you
Oh,
might not have time to do those things then. Because I have to give 5 assignments. I have given 2 assignments. I will be giving 3 more assignments for you to do. So I think you will not have time to do the other 3 assignments sometimes. So
Yep.
because of that, maybe yes, 27th
Yeah.
of Jan, I will leave it like that.
Yeah, it's always good to give you a shot.
Thank you.
Thank you.
Madam, can we do some tutorials or practical problems that to understand that how to apply these theories? And likewise, because for my case, madam, I referred your lectures and some referrals also the videos, but still I'm struggling to how to implement these things in practical situations and practical problems. But yes, ma'am. If you
So
can
I
at least upload the elements and then we can practice that and discuss for the other in other classes.
theoretical questions related to what I have discussed, right? I can do that. You mean practical means
the practical situation will mean that if it is that as an example in lectures you said that madam the telephone calls that we are receiving
yes.
and how to analyze these autocorrelations, correlations and these functions and how to apply these equations and get the things outputs. Yeah, likewise, madam.
Yes, I will try to make it more very practical applications oriented questions, and then I will maybe upload to LMS as you said. I will do that.
Thank you, madam. And another one, madam, in our last examinations, do we have the written exam or the Matlab or the both or just pay one paper?
Most of the time it will only be like a paper, written paper without including Matlab, closed book exam. So that will be like that. So I think there's LJMU and ECE. So you're from what group?
I'm from LGMU.
Okay, so for you, I think you will have 2-hour paper, closed book, written exam. No Matlab involved in there. So that's about it. About that.
Madam, yes.
Yeah, yes. So I mean, for the ECE students, it will be 3 hours actually. That's what. Yeah. Do you have other concerns?
When will be the exam?
Most probably it will be by the first week and second week of March.
Oh.
And madam, I have another one because I am a LGMU student, but
yeah.
I was heard that I don't know it's whether correct or not, but there's a problem with registration, our students registration in the LGMU, that means England University. And
Okay.
but still we haven't received any registration from the LGMU. And I don't know, we as students in the 4th batch of the LGMU, we email and we call, but no one is responding and giving us whether solid answer whether it is continuing with the LGMU or not, whether or not is there not or whether, but could you please that anyone here other than registrars, madam, that we can solve this problem, because still we haven't received any registration from the LGMU.
Yeah, so about that, I think if you can send me an email, I will forward it to maybe the dean of our faculty, and then I will ask him to, like provide some information regarding that. Can you send me an email?
Okay, madam.
Maybe I will forward it to you.
Okay.
Thank you.
Okay, thank you, madam.
With regard to the UGC approval for the ECE, I think I have requested my faculty dean to provide me some information. So he has informed our SLTC to like ask from the Ministry of Education about update regarding that, and Ministry has said that they are going to have a meeting, some SQA meeting this month, and then they will provide the update by the third week of this month, third or fourth week maximum of this month. So they will, have the meeting in this month. So they have been delayed due to some other reasons, I believe, but actually, may SRTC administration, you have to, I think we'll have to ask from that, because there was some kind of a like a change in administration persons in SLTC. So because of that only, that delay has happened. So anyway, I will keep you updated by the third week or fourth week of this month regarding the update in the UGC website. So I hope it is okay with you regarding that. I think many of you asked about that. So they will have a meeting by the third week of this month at the ministry, and they will update us on that by that time. So
Does it have to do anything with the exams timings, ma'am? Whether will it be delayed due to the decisions of
no,
the meetings?
no. The ministry it's a separate thing. So they are they're having the meeting, they are updating us, that's all. But we as the SLTC, we are just having the exams at the days that we are having. So for you, actually, we have to schedule the exams on that day, so we will have it. So I hope it is okay with you to have the exams on first week and second week of March. If you want it earlier than that, you can let me know.
Nobody
If you
wants
can-
exams
we
early.
appreciate if you can extend the exam date.
Yeah, so that was the most, kind of the best I was able to do, because I think it was supposed to start by next month, last week. So I
Oh,
think
How
now it's
about other
more.
modules? Same
For
thing.
all the other modules, also same things. I think within 2 weeks, we are finishing the exams for
Oh,
all the modules. So most of the time that will be done during Saturdays, 2 weeks, it will be done.
great. And will this is out of the advanced exams processing. Will we be given with um, supervisors for our research or the
Yeah,
project?
I'm sorry for not providing an update by this time, because I promised you that I will, but I will share because from my end I wanted to share it with you earlier than that, but still I did not share with with the possible supervisors kind of a like a document that they give their you know like ideas about the research topics that they want to work in. So they will include that, and then I will share those topics with you, and then you can decide like with whom you are going to do the research and what topic you want to work in, and also on. So currently you haven't started your thesis yet. The LGMU students, you haven't started thesis yet, or you have currently. What is your status actually? Do you have?
From my side, I started. I got a leave of absence. I am from the second batch of LJMU. I got a
Mhm.
leave of absence last year, And when I was getting the leave of absence, I already started with Professor Lasitya Seketu.
Yeah.
And then after the leave of absence, I didn't reach out to him, so I do not have any updates. I'm not sure if I can continue with that again, but let's see. Fingers crossed.
Yes. So I think I need to provide you the supervisors list by as soon as possible, really. So anyway, I think by this semester I will try to share with you so that you can start it at least by the next semester. So you have, I think, ECE students, of course, they have time. I think LGMU students, if you are already started and then doing, then fine. Otherwise, I think you need to find some supervisor as soon as possible. Also, before reaching out, if you have some idea for the research, then you can let the supervisor know, and then they can also they can easily try to work with you regarding that topic. Otherwise, you will sometimes have to also work under the research that the supervisor is specialized in. So anyway, like from my end, I will try to provide that document to you as soon as possible.
Do we have the freedom to select supervisors by ourselves, like the
supervisors means like the topics and supervisors will be given to you, so you can select both the topic and the supervisor basically.
All right, thank you.
Yeah, no problem.
Can we have some model questions before the exam, maybe a small revision?
Okay, I will provide you a model paper before the exam for both ECE and LJMU before the exam. So hopefully before the study leave period, I will provide it to you by the last week of the lectures.
Okay, thank you very much.
Will it be the same way around the last batch, like in the same format for the paper? Because I have seen in the LMS the past papers for last batches were there.
Yeah, I will try to follow the same format for the LJMU. For the ECE, I think I will create one, and I think I will, because this is the first time for the ECE, I will create it by myself and then maybe refer LJMU paper as well. Anyway, for LJMU, I will prepare in a certain format that they have requested to do so. So it will be similar to last time.
But if you want to make it easier, we understand.
Okay, yeah. Okay, no problem. Okay.
Just kidding. Thank you.
No problem. Thank you.